I'll start by talking about these two worksheets that I put up that talk about ways of constructing confidence intervals, just to illustrate the situation and why we have so many ways. So I talked about it as a hypothetical last time, but I want to sort of illustrate what's actually going on. Okay, so I encourage you to do some of these computer experiments. You can get a feel for it. So we're going to have some number of trials, 1,000 trials. You can forget about that for a second. So each trial is one draw from a binomial distribution. So you can think about it as, I get 1,000 people. I each ask them to throw 100 darts at the dartboard, right? And say that the probability of each person hitting the dartboard, have them stand far away, is just 10%, right? Which is pretty small. So as I make this smaller, the difference between as I make n smaller and as I make p smaller or large, close to 1 or close to 0, the differences between the different types of constructions will get bigger, right? So we'll be able to see it more easily. And then I'm going to do that 1,000 times, and the reason I'm doing it 1,000 times is so you can see what the outcomes kind of look like. All right. Then I do R binom, so I'm going to enlarge this font a little bit, if I can figure out how to do that.
Can you turn up the light in the front?
Turn off the light in the front?
Yeah, like
yeah, sure. That one? Is that better? Like that? Okay. Okay, so then I'm going to create a variable which just says, okay, do these 1,000 trials, get 1,000 people, have them each throw the dart 100 times with this probability. You can set it out. Okay, so the maximum likelihood estimator in this case is very simple. It's just the mean, the number of successes divided by the total. So we expect it to be around 10, but it's going to be different for each trial, right? So R is very sort of vector oriented. So okay, p hat is x, the vector of outcomes divided by the single number n, and it knows how to broadcast this n. And so this gives me just a vector of proportions, all around 10%. And then we saw that the formula for the Fisher information is this number n divided by p hat times 1 minus p hat. Okay, so that's the Fisher information that we're going to use to estimate the variance of the maximum likelihood estimator. Okay, so this is an untransformed maximum likelihood estimator, and we're saying that the Fisher information is equal to n divided by p hat 1 minus p hat. Okay, n times the Fisher information 1 over that I get from each observation. So the Fisher information is slightly different for each of these trials. And then the variance is just 1 over that. And again, this is doing a broadcasting. So this is a vector of Fisher informations. It's just for each vector, it takes the reciprocal for each entry of the Fisher information. And that gives me a list of variances, 1,000 variances, so I'm not printing them out. Okay. And so then this type of confidence interval, the walled confidence interval, is easy to estimate, right? It's just our MLE plus minus our U alpha, 1.96, that comes from our normal distribution, times the square root of the variance, or our estimate of the variance, right? Which comes from this. That's what we're doing here. The lower bound is p hat minus 1.96 times the square root of the variance, and the upper bound is p hat plus 1.96 times the square root of the variance. Okay, so that's our confidence interval, right? So why did I do this so many times? Because the point of the 1,000 trials is if this is a really good confidence interval, right, about 950 of those 1,000 trials, the confidence interval will contain 0.1, will contain the true value, and for the rest it won't. If the confidence interval is too aggressive, that number will be bigger than 0.95. If the confidence interval is too small, that number will be smaller than 0.95. Okay? And one of the things that forces it to be smaller than 0.95 is if there's degeneracy, right? So when I get an outcome where I only get someone throws it 100 times and they don't hit any, then it's going to cause, from your last homework, a degenerate confidence interval, which is just at 0, and that won't contain the true probability, which is greater than 0, and so that's going to contribute to the failure. So that's going to generally, because I picked one that's 0.01, that's going to pull the confidence interval away from 95%. Okay, so if it was good, this would converge to 0.95 as the number of trials went to infinity. So as n went to infinity, or the number of trials. Okay. So in other words, if I did this infinitely many times, or I look at it in expectation, and I take, so what does this say? It says take the lower bound, is the lower bound less than p, true or false, and the lower bound, or the p is less than the upper bound. So this just says, give me the vector, true or false, did the interval contain the true value? I take the sum of that, and so r is converting the trues and false to zeros and ones, and then I divide it by the number of trials, so this is the percent, or this is the fraction of times that it contained it, and it's only 0.936, okay? And that's not a fluke. If I did this many times, you would see that it was lower. So okay, so let's do that. So let's do what I just did, all the steps I just did, but let's do it 1,000 times, okay? So I'm saying this is the number of times I'm going to do that whole procedure. Let's do it, 10,000 times. So I do that, and I say, so I'm just making a vector to hold the answer. And then I say for I and 0 up to this number, just repeat the experiment I just did. Draw from the binomial distribution with 1,000 trials, n is equal to 100, p is equal to 0.1. Estimate the p-hats, estimates the Fisher information this way. Estimate the variance as 1 over the Fisher information, and then form the confidence intervals. In there is a vector which says, this vector, which I didn't give a name up here, this is the fraction of times that we were inside the confidence interval, and then store that in this vector. So I have a long vector which just has a bunch of these numbers in it, and then I plot that. I make a histogram of that conceptually. So what I actually am calling I want, instead of a histogram, I want a nice picture. Okay, so I could have said histogram, and then it wouldn't have looked very. So when I say density, that means it's using a kernel density estimator to smooth out the histogram and turn it into something that looks like a probability distribution. So that's what it looks like. Okay, so if it was really good, it would be centered over 0.95. But because there's a problem, which is there's degeneracy and the failure of normality close to when p is close to 1 and n is not big enough. In fact, most of the time this confidence interval has something more like 0.9, is more like a 93 or 94% confidence interval. So that's what it looks like when it goes wrong. So it doesn't work as advertised. Okay, any questions about that? And then I'm going to show you the one with the transformation.
Wilson interval. I'm wondering what's the difference between Wilson and log?
Right. So the Wilson, I think, is I may say this wrong, but Wilson is one of these other intervals that I'll talk about today. Sometimes I forget which one it is. I think it's the next one. If it's not the next, I think it's the next one. Okay. Yeah. So that's right. So in the SAS code, it was both Wilson and Wald, right? And I think the Wilson is the log transformed one, but you should check that. Okay, so this is the, all right. So let's go back to this one. Okay, so now, we'd like to improve the situation while still using this conceptually easy idea of a Wald-based confidence interval. Where I have some estimate of my value, and then I add and subtract some number to it, right? But now what we're going to do is use a transformation to try to fix some of these issues around p equals 0. Okay, so we want to begin in the same way. So I start by saying I'm going to have some trials, 1,000 people, each of which threw 100 darts and has a 10% chance of hitting. And then I make a vector r by nom, so these numbers aren't correct. I make a vector of outcomes, and then I make a vector of maximum likelihood estimates. And so of course, this thing, p hat, is a random variable that depends on the data and depends on the true value p, right? And we're going to transform this random variable into a different random variable, c hat, which is log p1 minus p hat. Okay, just a nice smooth transformation, and the point of doing that is to try to improve the performance of our confidence interval in the sense of getting it closer to 95%. Okay, so we're doing a change of coordinates, a nonlinear change of coordinates, and the goal of this coordinate is to eliminate these hard boundaries at 0 and 1 and hopefully smooth out and make the normal approximation work better. Okay, and so this is called a logit or a log odds transformation. And this is I'm just plotting the logit transformation. That's what it looks like. Right? So when we're near 0 or we're near 1, instead of hitting the boundary hard, we go off to negative infinity and positive infinity. So as p varies here, this is p, and this is the logit of p, or this is c. So that's the picture of the transformation that we're applying. Comes in the bottom and goes out the side. And now we're hoping that the distribution of the maximum likelihood estimator over the trials will look more normal here. Should show how that works. See, this is why I need to, let's see if I can get an administrator to install a browser from the 21st century. Okay. Well, I can say what this says. So, all right, so this is just applying this transformation. Phi hat, I guess I'm using phi, not c. Sorry about that. Phi hat is the log of p hat divided by 1 minus p hat. That's the estimate. And we also have to make sure we transform not just the vector of estimate, but our true value, our population value, which is now log p 1 minus p. Okay? So this is the true value, 0.01, or 0.1. And this is the estimated value from each trial. So this is the random variable that's moving around, and we have a vector of them, one for every trial, however many times the person actually hit the dartboard. And this is the true value, the 10% chance. And now so now we're basically done in the sense that we've transformed to a different coordinate system, this phi coordinate system, and now we just apply the same logic as before. So there's a theorem that you could learn if you take 553 that says that doing this transformation, we can still see that this thing is going to be asymptotically normally distributed. So it's kind of shocking. It's like we do all of this changes to these things. We can sort of brutally torture these variables, and they end up still normally distributed. There's a lot you can do without destroying that. Okay, so we can compute the Fisher information, and it's a little bit more subtle because we did a nonlinear transformation, so we have to use a little bit of calculus. I would take the derivative. So phi prime is 1 over p hat. Phi hat prime is 1 over phi times 1 minus phi. The Fisher information of p is n over p hat times 1 minus p hat. And the Fisher information vector is the Fisher information of p divided by phi prime. So this is just like a chain rule, right? We're applying a chain rule with this transformation. So we have to adjust our Fisher information to reflect the fact that we've changed coordinates. That's all we're doing. And then we can form a vector of variances in the same way as 1 over the Fisher information, and then proceed to compute lower and upper bounds for our confidence intervals. So lower bound again is it's just the same thing. In the phi coordinates, we have to use the phi hat as the center of our interval and the variance of phi hat as the variance. And then if this is good confidence interval, it should converge to 0.95 as the trials go to infinity. Now there's one trick we have to do here. So for the other one, we didn't have any transformation happening, so we didn't have to worry about what happened in the case that p hat was 0, right? So we're doing this kind of stupid maximum likelihood estimation where if I throw a dart 10 times and I hit 0 times, my estimate of my probability of hitting is 0, right? Which performs poorly when p is close to 0. That was fine as long as I wasn't trying to divide by 0, but now in say this one, right? If p is 0, then I have something n over 0, and that's going to cause not a number to come out when I do that in the computer. And so, but whenever that not a number came out, happens, what happened was just that, was that someone had a 0 in the trial, right? That particular trial had 0 successes. And so I'm just setting this to false or not in the interval whenever there was 0 successes, because when there was 0 successes, then the variance is 0 and the confidence interval is degenerate and it doesn't contain the true value, unless the true value happened to be 0, the true value of p. But in this case, we know the true value of p is not 0, so I have to set all these to false. So that's kind of a drag that pulls it back toward 0. But nevertheless, okay, this time, hey, we got 0.95. It worked pretty well. So let's do the meta version where I do this whole procedure and I do it 10,000 times. I construct the vector of outcomes. I construct the vector of MLEs. In terms of p, I construct the transformed vector of MLEs, the transformed true value, the Fisher information transformed, Fisher information of p, and the Fisher information transformed, and then construct from that our confidence intervals, and make this adjustment to make sure that it works correctly when we have 0 successes, and then we look at what we get. And, it's better. It's still not perfect, There's some funny lumpiness, and maybe this one's actually on the other side, right? Maybe this one includes it a little bit too often. It's not exactly 95%. But if you imagine this thing getting peaked and peaked, getting closer and closer as n goes to infinity, maybe it's like a 95.94% confidence interval or something like that. Okay, so it's a little bit better, and you get the idea of how doing such a transformation is going to change the performance of our confidence interval. And if I were to change in the previous example, if I were to change p to like 0.01 or something, the confidence interval would contain the true value only something like 60% of the time. So you can really see that it performs extremely poorly in that case. So that's why we say, if you can avoid it, use something better. So like these other intervals. Okay. So let's talk about what we do, what else we can do. Okay. So that's one thing we can do, is we can perform a transformation, which we hope smooths the situation out and causes our Wald-style confidence interval to perform better. But there are a couple of other things we can do as well. So let me turn the light back on. Oh, that's the wrong direction. Okay, so you can think about there being, as the sample size increases, we have a sequence of maximum likelihood estimators, right? You fix the true value of theta, let's call it, or the null hypothesis value. So let's fix the true value of theta. We have a sequence of maximum likelihood estimators increasing with n. And in a suitable sense, the sense of convergence of probability, which is not something we're going to worry about, but I'm going to write it just. A good maximum likelihood estimator is basically a root of the likelihood equation, so a place that's something which satisfies the first order conditions, and it's the right one, right? It's not the one that corresponds to a local maximum that doesn't go away. So if I have a consistent root of the likelihood equations, as n goes to infinity, this thing is going to go towards the true MLE. That's, we don't have that, then our estimate is completely useless, right? We want our maximum likelihood estimate to converge to the truth. And the idea is, if we're trying to test a null hypothesis, as the distance between the parameter corresponding to the null hypothesis, or the null hypothesis, and our estimate gets larger, and we should judge this distance based on n, right? If n is very large, even small differences are very significant. If n is very small, then it's not true. So as this distance gets larger, we reject, right? Or in other words, saying is we form a confidence interval around this thing. Right? These are totally equivalent points of view. So revect H0, theta naught is the truth, right? So the other techniques for constructing intervals or doing tests come from the observation, well, if theta naught is close, so to theta hat n, so if our MLE is close to the null hypothesis value, other things will be close as well. Namely, well, the likelihood of these two quantities should also be close together. Right? So if we assume that the likelihood function, or the log likelihood function is like something not too crazy, and we have theta naught and we have theta n, everything is continuous, and I look at the horizontal values, L of theta n and L of theta naught, those should also be close together. Right? Unless our likelihood function is just completely bonkers, in which case nothing works. Okay? So as these things get closer, these two get closer. And also, we chose our MLE by solving the likelihood equations, that is, by looking at this first order conditions. Right? So we set, in other words, this thing, or we would think about this as being the solution to L prime of some theta is equal to 0, right? If this is our log likelihood, we chose a point where the derivative was 0. Right? So it satisfies that. If it didn't, then we would choose the one that was slightly different, right? Assuming it's differentiable and nice. All right. So that means that, so if theta is close, theta naught is close to our estimate, then the derivative of the likelihood function applied to theta 0, the null hypothesis, should be close to 0, because that's equal to L prime of theta hat n. Right? So these two ideas, instead of measuring the distance between the parameter and the null hypothesis, or the transform parameter and the transform null hypothesis, instead measure a function of them, like the difference in the likelihoods or the value of the first derivative at the null hypothesis, leads to two different types of hypothesis tests or two different types of confidence intervals. Okay? And these are very cool ones for a number of reasons. One is that both of these, the tests that these two things generate, so this is the likelihood ratio test, and this is the score or Rao test. The tests they generate, you could ask them, well, what if you do a transformation? Right? Does that give you something potentially better, just like we saw? And the answer is no, because remarkably for these, because it goes through the likelihood, it sort of corrects for the transformation. So these, it does not depend on the particular coordinate system we chose for theta. So if I change coordinates, if I do a trick like the logic transformation on theta, it will not change these answers at all. So one of the appeals of these is that you don't have to worry about whether you picked a good coordinatization, a good coordinate system for your theta. Right? There's no way you could do any better. It just doesn't care. The other nice feature about this one is, if you'll notice, what we're doing is measuring the value, this value here, L prime of theta naught. And as opposed to all the others, what is that one missing? There's a quantity that doesn't appear in that. Tell me what that is. I shut this down. So what doesn't appear in that score function that appears in the other two? So we have this one, null hypothesis versus the estimator. That's the walled. We have f of theta minus f of theta. This is the transformed walled. And I can choose lots of different transformations, and there's an art to choosing those. Then we have the likelihood ratio, which compares these two numbers. Then maybe we want to take the absolute values and things like that. I'm ignoring that for now. And then we have this last one, compare the derivatives, except that we don't need that because we know it's 0. And so we just, okay, so it's just this number, right? That's our metric, okay? So what's missing from this one that appears in all these others? Yeah, right. So one of the appeals of the score test is that it depends on the data only through the construction of the likelihood function. You take the data, you build your likelihood function, take its derivative, and you take your null hypothesis, and you never have to figure out what the MLE is at all. Right? So that's kind of beautiful, because in some cases, right, if you have one of these problems that's fairly complex, where the likelihood function is nasty, it might be quite hard to get an MLE, right? So like if I have like a bumpy likelihood function, I don't have to worry about this problem of am I at the right peak or not. That problem goes away, because I don't have to find the MLE here. And one of the things you'll see, so one of the things we have to do is, for each of these, so this one we've already seen, this one we've already seen, for each of these we have to estimate a variance, right? In order to form a confidence interval. So these are fairly straightforward. We have to estimate this variance and this variance. And when we estimate a variance, we have some choices as to whether we use the null or we use the MLE. So in this one, usually, in these we kind of interchangeably estimate the variance using either the null or using the MLE. In this one, we'll usually choose to estimate using only the null so that we don't introduce dependence on the estimator. Okay, so I should say also that underlying these is some asymptotics that we won't talk about how to prove. If you're interested, I'm going to write down a reference. So Dave Hunter, the chair of the stats department here, has some online notes on titled, I think, Asymptotic Tools. There's lots of other places you can look this up as well. And that's for a class we have here called Stat 553. And this covers, if you want to learn more about the details of why these things work, it covers everything that I'm talking about today. Sort of the mathematical details of why these things work in great detail. But in, for example, this paper and this thing in theorem 7.8, it says that under suitable regularity conditions, we have a nice probability distribution with a function that depends in a nice way on theta. Under regularity conditions and under the assumption that the null hypothesis is true, then the square root of n, theta hat n, this is the estimator as the sample size increases, minus theta naught, the null hypothesis version. And the null hypothesis is true, so that's the true value. This is going to converge in a certain sense called converging distribution. So we're talking about a random variable which is converging, because this part is random, the other parts are not, which is a certain sense in which a random variable to converge to a normal distribution with that variance. So that means 0 and the variance 1 over the Fisher information at the null hypothesis. Okay. So this is saying if I make this correction to this difference by the square root of n scaling, then as d goes to infinity, it's going to form a nice bell curve with this variance, and that's why the confidence interval works, essentially. We're assuming that n is large enough that we've gotten close to this. Okay. And for the other ones, it's different scaling factors, 1 over root n. times the score function, the likelihood of the true value, theta naught. This is going to converge in distribution to n0I of theta naught. So that's the variance here. So remember this one, we're only ever really going to use this Fisher information. In this one, we'll sometimes replace this with an I hat that's estimated from the data. And lastly, minus 1 over n L prime prime of theta. So this is not telling you, this is talking about a second derivative, but what this is telling you is that it's okay to estimate this with this. There's got to be an n here. That's there. Okay. So this is telling you if you want to replace the I of thetas here with I hats that are estimated from the data, expected, observed information instead of expected. This is expected information. If you want to replace it with observed information, that's okay asymptotically as well.
Sorry, what's the P stand for?
It just means convergence in probability, which is a stronger kind of convergence than this, which is convergence in distribution. Yeah, but don't worry about it. I mean, that's certainly not part of. If you care to learn about the differences between different types of convergence, I encourage you to look it up. Basically, you can think about this is a single quantity. This is just a number, right? It's converging to a number, whereas this is converging to a distribution, right? So the notion of what does it mean to converge to distribution is a little bit subtle, but you can sort of imagine what it looks like, right? It's like it starts out kind of bumpy, and it gets better, and it gets better, and it gets better. Whereas this is saying it's converging to just a point, a trivial distribution or Dirac delta.
That's like the central limit theorem?
Yeah, they use the central limit theorem to prove it, right? But I'm just saying, even the notion of what does it mean for one probability distribution to be close or far from another, and what does it mean for it to converge to another, is a little bit like technical. You know, like you have to be very careful about. You see measure theory and like worry about exactly what your definitions are for that to make sense. But details are given in there. Okay. So that means we get, so given that we get statistics, test statistics, or equivalently procedures for constructing confidence intervals. So our walled test statistic is root n I of theta naught, which because of this, we can replace this with I hat, like the information of the MLE, if we want. That times the difference between the MLE and the true value at the null under the null hypothesis in the sense of convergence of probability distributions goes to n01. It's just restating this essentially. And so that means this is why we can say, you know, if we want to do a test, we can use the values that come from the normal distribution. Right? And for the score test, we have another statistic which you could call a Rao or a score statistic. Rao is a nice name to use because he works here. We make the adjustment for the variance, scaling factor, multiply that by the derivative of log likelihood at the null hypothesis value, assuming that the null hypothesis is true, that's going to converge to n01. So that tells us that we can use that statistic or those standard normal numbers to construct confidence intervals. Okay, so a walled test is one that accepts or rejects or forms a confidence interval based on this statistic. A score test is one that accepts or rejects or forms a confidence interval based on that statistic. So if this number is bigger than, the absolute value of that is bigger than 1.96. it would be outside the interval. So the sort of asymptotic calculation is a little bit more subtle for the likelihood ratio, and I won't go through it. But the idea is that we want to compare, we have some difference between the likelihood at the MLE and the likelihood at the true value or the null hypothesis value. And a small calculation, again, if you want to read the calculation, you can look at these Hunter notes, page 162, 163. It's like a 6-line argument that does a Taylor expansion. So if you do that, you get that twice this number, twice this difference, and maybe I want to take the absolute value, converges in distribution under the null hypothesis to the chi-squared distribution with 1 degree of freedom. Okay, and this 1 here is secretly dim of the parameter space, the dimension of the parameter space. So if you don't, so the degrees of freedom corresponds to the dimension of the model. So one reason we care about finding dimensions of models. Okay, so then you can, of course, since the chi-square distribution is closely related to the normal distribution, you can look at its quantiles as just the ones from the normal variate n squared. So a likelihood test is going to be a test which rejects, say which just to be clear, a likelihood ratio test rejects the null that the parameter is equal to theta naught in favor of an alternative that the parameter is not equal to theta naught when 2 delta n is greater than or equal to u alpha over 2 squared, or equivalently when the square root of 2 delta n is greater than or equal to alpha over 2. So these are just these numbers like 1.96. Comes from the normal distribution. Okay. And is it clear why it's called a likelihood ratio test, by the way? I didn't write any ratios there.
Not really. I'm kind of confused about it. Because I made likelihood ratio test before. Like, they're usually like.
There's a ratio. Well, how would I write this out? In terms of likelihood, what would that be? Log L theta hat n over L theta naught. So that's why. It's the ratio, it's a log of the ratio of the likelihoods, which just becomes the difference. Probably when they first did it, it was really literally the ratio, and then they found that it was better to work with the logs. Okay, so one of the things that happens is that, when our sample size gets big, so all these n's, when n's go to infinity, in the super long run, everything is always okay, right? The heat death of the universe, and all our assumptions are satisfied. So when n goes to infinity, all these hypothesis tests will agree. Right. And if I wanted to relate that to the pictures that we had up a minute ago, that's n going to infinity, not the number of trials or the meta thing, right? So that's the actual n going to infinity. So if I let the n go to infinity, then even if I hold p to be fixed, right, and I let n go to infinity, then there'll be enough space around p for the normal approximation to hold. It's like we zoomed in, right? So we have some kind of, this is p, and then we, so when n is small, it's like we're too close to 0 and bad things happen. But when n is gargantuan, right, n is 100 billion or something, 0.01 times n is actually pretty big. And there's plenty of room on both sides of it to get the normal approximation. Okay, so that doesn't contradict at all what I said about the confidence intervals before. So as n goes to infinity, all of these hypothesis tests or all of these methods for creating confidence intervals give the same answer. But for small sample sizes, such as those that occur in your actual data, they give different answers. As we've seen, the performance can be different. And in fact, you can use it as a diagnostic. Right, so it's imperfect, but it's kind of a heuristic. But if you do all these hypothesis tests and they all give more or less the same answer, well, then maybe we're close enough to infinity. Right? It's evidence, at least, that we're close enough to infinity. If they all give wildly different answers, that's information that says, hey, we're pretty far from infinity. The sample size is small enough that it matters which test I do. So be careful. Okay? So you can use the fact that these don't give the same answer as a way to tell whether your data is big enough for asymptotic assumptions to hold. Any questions?
What is the U alpha over 2?
Oh, just like the cutoff. So if I wanted p equals or alpha equals 0.05, then this would be 1.96, like that. It's the cutoff that we use to say that standard normal contains 95% of the. Okay, so why didn't I give you a quick picture of how to calculate the intervals for these other tests? Why do you think I didn't do that yet? Is it clear how you would create that interval? So say this is my criteria, right? I want this number to be smaller than that, right? I'm trying to create a confidence interval, say. So how do I decide which parameter values fit that? Which parameter values, what's my upper and lower bound from this? Yeah, right. I mean, there's no formula for it. That's the point, right? So there isn't really a formula for it. It's just you have to kind of look at the, right? So it'll be something like, oh, here's our likelihood thing, and here's our maximum likelihood, and it has some value, L of theta hat n, and we want to allow everything which is below it, so that the delta, so the difference between that and some other thing, L of theta naught, is some delta n, right? And we're saying we're going to pick delta n. So that's why in the notes we'll say, okay, we draw a horizontal line. Right? So we have to say, okay, we're bounding this distance to be no bigger than something. And then we have to look up on our graph to find what these are. Okay? So you sort of have to invert the likelihood log likelihood function in order to extract the intervals from that. So you probably need to use a computer to do that, unless you have a very nice form for these. But in general, you'll have to ask the computer to do it for you. So maybe I'll do that next time. But I'll just be calling some function that does that, or walking you through how to do that. Okay. So one of the advantages and disadvantages of these things, that tells you that one of the advantages for the walled type tests, the walled and transformed walled, is that you don't have to do any of this craziness, right? You just add and subtract something to it. So an advantage is that it's easy to construct. And that's one of the reasons that we teach them in introductory statistics classes. Construct and interpret. And that's really, that's kind of their appeal. More that it's easy to construct them than that they actually work well. And the other thing is that well, it's easy to see what to do for a one-sided test because we're just adding and subtracting. We can just choose to adjust our test for one side, whereas for this, how to construct a one-sided test is a little bit more subtle. I have to think about it a little bit. So that's what's nice about the walled test. The score test is nice because we don't need the MLE. Right? So that simplifies our calculation. And if we're in a situation where the MLE is hard to get, but the score or even an approximation of the score is easy to get, then we're still in business. And the score and the likelihood ratio are both invariant under reparameterization, which is sort of both good and bad, right? It means we can't use the reparameterization trick to improve them, but we also don't have to worry about the coordinates that we chose, right? We're not going to get a different answer if we take the log of our parameter, or we take a logistic transformation, or we do anything else. Okay, so as to which to use, well, I'm going to punt on that for now. We'll talk about that a little bit more later. And to some extent, it depends on the specific characteristics of your data, whether n is big, whether sort of cells in the data are big. I'd say that very, very often, if you stick with that one, it will be, that's probably, if you had to pick one without knowing anything else, I'd probably pick likelihood ratio in terms of something which is likely to best perform. But there's an R package, for example, called PropCI, which is devoted entirely to different methods of constructing confidence intervals for binomial distributions, right? Estimating proportions. And that contains a bunch of different routines. It has some of these routines, but it has other carefully thought out and dirty trick strategies for constructing these things. And Agresti is actually one of the people that has come up with some of these methods for constructing confidence intervals. So one of the answers is you look at what other people have done for similar data and have found to work well and use that. But if you have to make a choice without knowing anything, I'd say try the likelihood ratio. Okay. Let's talk about the obligatory binomial example for these guys. So it's not that we care that much about the binomial stuff. It's just that it's easy to calculate and understand what's going on. Most of the time we'll be applying these tests to more complicated distributions. But it's nice to just have something to compare things to. Okay, so the binomial log likelihood looks like x log p n minus x log 1 minus p. A likelihood ratio test statistic is then 2 x log p hat over p0 plus n minus x log 1 minus p hat over 1 minus p0. That's our 2 delta. And here the p0s are the null hypothesis, assuming the null hypothesis is correct and all that. Our score function, L prime of p, is x minus np over p 1 minus p. And our score statistic is p hat minus p naught over the square root of p naught 1 minus p naught over n squared. That's just the result of applying those formula to the binomial distribution. And I already mentioned how you construct intervals, and there's some code for this in these 2 drinking.r and drinking.sas. Gives some examples, some code for how this works. So for example, if you wanted to repeat the experiment that I showed on the computer for these other tests, it would tell you how to do that. Okay, any questions? And I'm going to start the next part, lesson 2, or what's under lesson 2 in the online notes. So the lessons will correspond roughly, but not precisely to the weeks, as things go over and under. Okay, so we're sort of building up more and more sophisticated models over the course of the term. And eventually we want to get to many-way tables, as we spoke about in the introduction. First we talked about this kind of binomial thing, which is like the simplest possible thing. It's a one-way table with 2 outcomes, right? Win and lose. And we put counts into it. And we fix n. So n is 30, and maybe this is 10 and 20 or something. Right? And it's 1/3, and we've talked about how to do inference for that. Okay, so the next thing we could look at is a one-way table. That is, this is an example of a one-way table, but instead of only one category, we have many categories, red, green, and blue, say, or whatever. Many different ordinal or nominal categories. I think it's just nominal for now. Well, nominal or ordinal, depends on we'll see both examples. And one of the things, this seems very simplistic, but as we mentioned in the very first class, there's kind of an interrelationship between the notion of a one-way table and the idea of a multinomial distribution. So every table, no matter how complex, can be, if I had a 2x3 table, of course I could convert that to a one-way table by just giving each cell its own entry, right? So RW, RL, RG, GW, GL, BW, BL. Right? And that's, of course, just like in the computer, there's no such thing as an n-way table. There's just arrays. It's just long chunks of memory. And just like the computer only thinks about it this way, we can always choose to think about any table as a one-way table. Of course, when we do that, we give up information. We give up information about how that table is broken up. But we can think about anything as just a category with types. And now there's sort of 2 fundamental types of data that appear in one-way tables that we'd like to consider that correspond to different ideas about how the data was generated. And this is very much about our perspective on it, more so than it is about the data itself. So, okay, let's give an example. Okay, so here's a one-way table. And let's put some numbers in it. 10, 13, 23, 7. Let's give it one more. 4. Okay. Now I could think about this as being, say, colors, red, green, blue, cyan, and magenta, or something. And I can think about the total, which is, this is annoying to total up, right? 11, 34, 47, 57, right? So we can think about the total, 57, as fixed. And then, so we have some number n, like number of trials or number of darts. And then we get, which ring of the dartboard it landed on, right? So that's multinomial. So we're thinking of the data as being sampled in a multinomial way. Right? There's some probability of it landing in red, green, blue, cyan, or magenta. There's some fixed sample size, and we do our inference thinking about it that way. The other thing we could think about is that this n equals 57 is just sort of a coincidence, and what was going on was, we fixed a certain amount of time. Like maybe this is a 5-sided die, if such a thing can exist, and we rolled it, or it's a computer random number generator that likes to screen one of these things, and we just hit the key over and over again for some period of time, and we counted how many times it came out, right? So then n is itself a random variable, right? And that's a Poisson sampling scheme. So the same table can be thought of in different ways as a multinomial or a Poisson, depending on how we're interpreting the data. And as that suggests, for lots of tests, we can sort of switch between these things. If we don't care about doing inference on n as a random variable, we can forget that it's a random variable, call it fixed, and look at multinomial statistics. Right? So a more natural or another example of how Poisson table, one-way table can arise is if this thing is ordinal. So, suppose we have, like in our first homework, we had this ships example. So we have number of ships observed, and it could be 1, 0, 1, 2, 3, 4, 5, maybe 6 or more. Right? The homework was about less than 5 ships. And we have a count. So this is our table, and we have some number that appears, right? So it could even be the same numbers, 10, 13, 23, 7, 7, 4, maybe 0, 0. So, okay, so it's sort of the same numbers that appeared over here, but now it has another interpretation, which is that I'm thinking about this as being a Poisson, but it's kind of a Poisson with one cell, and this is just a way of interpreting the data. Okay, so let me say this. This is an example, which is the notes, which is a good example. It's a little bit clearer, so let me just talk about that for a second. So suppose I take a 6-sided die and I roll it. If I roll it n times and I look at the outcomes, how many times it came up each number, maybe it came up 5, 5, 6, 4, 3, 7 or something. Then I'm sampling from a multinomial distribution. If I roll it for 2 minutes, and I total it up, then I'm looking at this is multinomial sampling. Then it's Poisson, because in this one the total number of rolls varies. Okay, so is those clear differences sort of clear? It's not that complicated really, but it's something to keep straight, kind of. Okay, so if we were thinking about, let's say it this way. So we were thinking about this, say the dice example, like a loaded die or something. If we were thinking about it from a multinomial point of view, what would the parameter that we were estimating be? Or parameters?
Do you mean like it would be multinomial 30 and then 1, 6 for each?
Right, so that's a, so okay, let's move right back down. Right, so this thing here is our parameter vector, right, or our joint distribution. Or a joint distribution. Right, so this might reflect, for example, the 1, 6, 1 might be the null hypothesis. So an example of a test that we would like to do might be, is this die fair or not? If I roll it 30 times and I observe this outcome, obviously these proportions are not exactly equal to 1/6, but they're pretty close. And I can ask the question, are they statistically significant? Is there deviation from this statistically significant or not? So I can do hypothesis test. I want to do a hypothesis test. Right, of the empirical distribution, and the null hypothesis. Another thing I might want to do is to just, for this it's easy, but in general it's a little bit subtle, is I might want to estimate this p hat. Right? I might want to find a maximum likelihood, usually estimate of what I think that parameter is. And the other thing, which is hard to see in this particular example because it's kind of empty, is test model fit. Okay, so what do I mean by that? Well, if I have a multinomial model where each of these probabilities is allowed to be vary separately, will that model always fit the dice example? If I roll a loaded die n times, can I always fit a multinomial distribution to that? So for example, suppose I get this outcome here. What would be your maximum likelihood estimator? Take a guess. 5. All right, so it should be a vector of 6 numbers. What 6 numbers should I write? My MLE for that example. 5. Divide them, right? So I have to divide them by, I just convert that to proportion. So my MLE for this, if this was my x, my MLE will be 5 over 30, 5 over 30, 6 over 30. I didn't prove this is the MLE, but I'm sure you'll believe me. 4 over 30, 3 over 30, and 7 over 30. That's my p hat. Okay. And if I had seen a different outcome, I could construct a p hat. So this is certainly a multinomial distribution. And assigns a probability to each outcome, and they sum to 1. If I saw a different outcome, I could fit another multimodal distribution. So the model fit here is just not an issue, right? So the model always fits. So that's one of the reasons that the multinomial on this kind of one-dimensional thing is fundamental. The model will always fit it, right? There's always a multinomial that I can choose. It's just the empirical probability distribution. Okay. But if I added restrictions to the model, it might not fit. So for example, I could say, well, instead of using this 5-dimensional model, right, there's 5 free parameters, and the last one is determined. I could use one that said something like, well, I have parameter p and q, and I think it's p, 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 q, q, q. Right, so I only have 2 parameters now to fit instead of 5. And now if I see something that looks like, if I see an outcome like 5, 5, 5, 10, 10, 10, now I have a different total, but okay. That's fine, that fits. But if I see an outcome like 100, 1, 50, 100, 1, 50, chances are this is not a good fit for this model. So as soon as I make my model such that it doesn't represent all possible probability distributions, model fit becomes an issue. And I need a strategy for measuring, to take all possible points. I can think about this thing as being some space. And I can think about my data as being out here, and I say, on this space of all possible models, P and Q, how far is my actual data from that model? If it's far, then I reject the null hypothesis. If it's close, then the hypothesis that it's on the model. If it's close, then I accept it. And so the whole sort of business of fitting models and chi-squared tests and things like that are sort of all about this problem, right? I have some model, which is sort of like a lower dimensional space. It's like a surface in a 3 space or something like that. My data is out there, not on the model, and I just have to decide, is it close enough to plausibly come from this or not? How about if it was a Poisson? What would be the parameters that you were estimating? If I was thinking about this as this vector, I didn't roll. I rolled for 2 minutes, and I saw those outcomes. What would be the parameter vector for a Poisson? Something different, right? So maybe think of dice, which has this weird exclusivity thing. Think of something, I don't know, maybe I have, I'm counting the cars that are coming by, and I'm counting what color the cars are. Right? Are they silver? Are they blue? Are they white? Are they red? I'm not going anymore, it's not going to be this model anymore, right? It's not going to be a multinomial, it's going to be something else.
Each car, you're trying to estimate its parameters.
Right.
Each one.
Right, so we're saying that we'd be assuming that they're independent, and we have just a vector of lambdas. Lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6. We're trying to estimate this vector of rate parameters, and we're also interested in the sum of them probably, which is the total rate. Forgetting color, number of cars, just number of cars. And this one is kind of the thing that kind of plays the role of n, right? This controls n as a random variable. Then you can see how by playing a trick with this, we can sort of decouple, right? We can say, okay, let this be random and multinomial kind of fixing n. So you can sort of decouple the Poisson aspect and the multinomial aspect. Okay, so unrestricted sampling like this, where the sample size is not controlled, but there's some other factor, like time or space, is Poisson sampling. We're trying to estimate the rates. When I fix the sample size, we're in a multinomial or binomial sampling scheme. In both cases, we can ask questions about fit, right? So this is the saturated model for the multinomial. Everything fits. If I restrict my model, some things fit, some data points fit and some don't. Of course, I could do the same thing here with the cars. For example, I could say, well, I only have, instead of having 6 parameters, I only have 2, red or not red. And then I could ask whether the data matches up with that, right? Whether it's plausible that the data could have come from a vector that was like lambda red, lambda red, lambda red, or well, there's only one red, I guess. Lambda not red, lambda not red, lambda not red, lambda not red, lambda not red. Which is sort of another way of saying is there only 2 parameters really going on. And if these vary too much from each other, I could reject that hypothesis. If these are all fairly similar, and this one is different, then that seems fine, right? Okay, so in this Poisson case, we're making an assumption in order for this to work. And then we'll talk about what happens when those assumptions are violated. That is, we're assuming that there's independence among events. So one car coming doesn't increase or decrease the probability that another car will come right after it. There's a homogeneity assumption. So that is that all seconds are equal. So if, for example, I'm talking about cars traveling over the course of a day, and I look at number of cars arriving in an hour, this is probably violated because some hours have more cars than other hours. So these rate parameters change. If the rate parameter changes, then homogeneity is not satisfied. And the last thing is, this is kind of implicit, but we're fixing the time period, right? We're looking at all the same amount of space at the same amount of time. It's just this fixed period on the bottom. Okay. And again, the last thing I want to mention is that when these violations, these things, well, okay. It's easy to measure or note when that is violated, and it's frequently violated for the Poisson. And the reason is that for the Poisson distribution, lambda, it only has one parameter, lambda, and the expectation of the number of observations is lambda, and the variance of the number of observations is also lambda. And so if you see a situation where the mean rate is below the variance, which is fairly frequent, that probably meant that there was a failure of one of these assumptions, particularly homogeneity. Right? So if for example, this is time, and this is this is rate of cars, so per second. So I break my data into seconds, and this is 9 a.m. and this is 5 p.m. So there's a higher rate of cars around rush hour, and there's a higher rate of cars around rush hour. This is going to cause variance to exceed the mean. Okay, so the mean will be, I don't know, here, but the variance will be a larger number. And that's this idea of overdispersion. And there are two strategies for overdispersion that we'll look at. And they're fundamentally, either you try to explain it, so you say, okay, the overdispersion is caused because there's some variable I didn't take into account, like whether it's rush hour or not. That's obviously much better. You try to explain the hidden variables that's messing up your data. Or you can say, it's too late, my experiment is done, all the money is spent, and I can't measure anything else. So I just have to assume there was some variable which I'm not going to look at and model that. So you can do that too. So basically you add a parameter for variance. You say there's some unknown, I don't know what the unknown is, but it's causing the variance to get pumped up, and I'm not going to try to explain it. So you sort of weaken the assumption of Poisson. So you want to try to explain it by some kind of regression or something if you can, but if you can't, there's sort of a way to proceed anyway by just assuming that there was something you didn't see. Okay, so that's all for today, and you have a homework which was due Sunday, but you maybe didn't hand it in yet, so don't forget to hand it in today. There's a new homework that was posted yesterday, and we'll see you on Thursday.